Okay, so separating or isolating things through differences in volatility. So volatility we know is related to IMFs. It's not a physical property they ask about a lot on the IB exam, but they do sometimes. And volatility is basically a measure of how quickly something evaporates, and it's very closely related to a property called vapor pressure. Vapor pressure is the amount of pressure that builds up above a liquid when it's in a sealed container. So if you seal up water, and you're at a certain temperature, like room temperature, a certain amount of water will evaporate and fill the space above the liquid water, and you can measure that amount of pressure, and that's what's known as the vapor pressure. Now, if you warm the water up, more of the water will evaporate, and it will therefore create more pressure from its vapor. So vapor pressure goes up with temperature. And molecules that have weaker IMFs have higher volatility, they evaporate more readily, and therefore they also create higher vapor pressures at the same pressure. So something like ethanol or acetone that evaporates more readily than water will have a higher vapor pressure value at the same temperature as water because that liquid evaporates more, so there'll be more gas molecules in the gas phase at the same temperature. Okay, so what affects IMFs? As a reminder, we know that increasing surface area makes stronger IMFs because of increasing London forces, and we also know that polarity affects IMFs. So thinking through from hydrogen bonding being the strongest, to then dipole-dipole forces, to then London forces being weakest. Now we can exploit this in a process called fractional distillation. We've talked about distillation before, simple distillation, where you heat a mixture and the liquid, the component with the lowest boiling point, is going to vaporize first. You can connect it so it has an elbow, and so as it vaporizes, the gases end up in this tube. They start to travel down this tube, and you surround this tube with water. You usually have it connected to running water so it stays nice and cold, and so that causes condensation of the gases, and then you can collect them over here. So it allows you to collect and separate off the components that have the lower boiling points and leave behind the ones that have the higher boiling points. But every time you distill, it's not going to be perfect. You're not going to get 100% of the component with the low boiling point and 100% left behind the one with the high boiling point. You get a mixture. This is why alcohol companies like whiskey companies talk about triple distilling, because they have to distill the alcohol 3 times to get it really, really concentrated. And that's what we're going to talk about right now. But first, we'll look at these different kinds of distillation columns. These are called fractioning columns. And the difference between this and normal distillation is that these have a lot more surface. And so as things begin to vaporize and move away from the heat source, so the heat source is at the bottom here. So as they move away from the heat source, it's going to get colder the further up this column we travel. And every time that the gases start to hit these beads, in this case, it gives them an opportunity to condense, because when molecules hit surfaces that are a little bit cooler, like we know water does this, it will turn back into liquid. And so by having all these little beads in this column, you get a series of evaporations and condensations, evaporations, condensations, evaporation, condensation. So by having lots and lots of surfaces, you increase the amount of cycles of evaporations and condensations. And basically what a column like this does is it really amplifies any differences in volatility. So if you just have the single vessel in my beautiful drawing over here, it's going to be harder to separate out things that have somewhat close boiling points. But if you want to separate things out that have relatively close boiling points, by increasing the surface area with these more complex fractioning columns, you can make things separate out that have smaller differences in boiling point through the many cycles of evaporation and condensation. This is just a different model where the vapor can escape here, but then you've got different chambers by which it can travel through and also condense back down. Okay, now this relates to the medicine topic because in a couple ways. One, this model here, or even these other ones, these could be used for recycling solvents. We could distill and we can recollect solvents. That's kind of a green chemistry initiative, not wanting to create a lot of solvent waste or not wanting to have to incinerate solvents and make CO2 emissions. So if we distill them, then we can recollect them and we can recycle them. Or this could be that the precursor molecule or the drug molecule itself is perhaps in the liquid state and perhaps it's more volatile, or it's mixed with something else that's more volatile. So this would be a way of separating out components if you're trying to isolate some sort of medicine or precursor molecule. So you can use this for separation of components. And so instead of separating them based on solubility, we are separating them based on volatility. They're both related to IMFs, they're just slightly different techniques. Final thing is they make this a little bit more mathy. I think questions on this are going to be pretty rare. It's not really that closely, obviously, linked to the medicine topic, so it's not going to be that common of a question. But there's a bullet point about it on the syllabus, so we need to cover it. Okay, so the basic idea is just that when you have a mixture in the liquid phase, so aqueous mixture or two other liquids together, there's going to be a ratio of the two things in the mixture. And we're mainly just going to look at mixtures that have two components. So for example, if you've got water and you've got ethanol. So you've got two components in this mixture. Now let's say it's a 50-50 mixture of water and ethanol. Well, related back to volatility, if you seal off this container and you were able to zoom in on the vapor would have more ethanol than water. It would have some of both, but if I totally make up numbers right now just to make my point, not prove my point, but just make my point, if you have like a 50-50 liquid mixture, you'd end up with a higher percentage of ethanol in the vapor because ethanol is more volatile, it evaporates more, so you'll get more of it in the vapor phase. Now, this idea, this relatively simple idea, can be quantified with something called a mole fraction and the vapor pressure values. Okay, so a mole fraction. A mole fraction is looking essentially at percent composition of a mixture, but instead of looking at it from percent by mass, it's looking at percent by particles or percent by moles. So as an example, if you have a mixture that has 0.2 moles of component A and 1.8 moles of component B, then we can see that basically 10% is A and 90% is B in terms of the particles, in terms of the moles. So a mole fraction is really just looking at a percentage out of the total moles, but it's not written as a percentage, it's written as a decimal. We've got a mole fraction of A is 0.1, and we've got a mole fraction of B is 0.9. Okay, now if I go to a harder question to finish off, if we start with the gram amounts, so if I have a mixture that has 250 grams of water and 250 grams of ethanol, what is the mole fraction of each? So the first thing we have to do is convert these into moles. So if we divide by molar mass, I get 13.9 moles of water, and I get 5.43 moles of ethanol. So in total, the total amount of moles is 19.33. So if I want to get their mole fraction, I would have to divide each by that 19.33, which is the total amount of moles. When I do that, I get a value of 0.72 for water, and I get a value of 0.28 for ethanol. So this mixture, although it was 50-50 by mass, when we look at the actual number of particles, there's about 72% water molecules for only 28% ethanol molecules. Okay, so that's in the liquid phase, that's in the aqueous solution. Now, if we look at their vapor pressures, we can tell that at 20 degrees Celsius, since water has a lower vapor pressure, that means it's less volatile. It doesn't produce as much vapor, whereas ethanol is more volatile. And so there's a way to calculate the pressure that each one is contributing. And you basically just have to take its mole fraction, which is this 0.72 for water, and you multiply it by the vapor pressure. And that tells you how much pressure will be contributed by, in this case, water. So when I multiply these together, I get 1.7 kilopascals. So water is contributing pressure above this mixture of 1.7 kilopascals. And the ethanol is contributing 0.28 times 5.95. So it's contributing 1.65 kPa. And so in total, what's the total vapor pressure is the combination. And so we get 3.45 kPa as the total vapor pressure. Now, if I look at those partial pressures, is what we call these, the pressure from the water and the pressure from the ethanol, I can see that it's almost 50-50. So although the liquid mixture had almost 3/4 water, the vapor now has about 50-50 of the two components. And so this is kind of backing up with numbers the idea we talked about before with distillation. When I vaporize this mixture of water and ethanol, even though at first there's only 28% ethanol, if I vaporize it, I'm going to get to about 50% ethanol in my first distillation. And so then if I distill it again, I'm going to again increase the percentage that is in the ethanol. So with each round of distillation, we're going to keep increasing our percentage of the more volatile component. And that's really the idea behind this. That's kind of as much time as I'd want to spend on the quantitative aspect of mole fractions and partial pressures.